Write 2-3 points related to alums. Alums are, anyone? They are double sulfates. So somebody should fill the ink. None is functioning. But it is this pen.
Yes, sir.
But it is going now.
No, sir, nothing.
Which one? This one?
Yes, sir.
To come back?
Come back, give this one.
Okay. So regarding alums, the first point you should know, they are double sulfates containing what? A univalent cation and a trivalent cation. For example, the common alum or potash alum. K2SO4, Al2SO4, thrice 24H2. This is called common alum or potash alum. So what is the univalent cation here? K plus. What is the trivalent cation? Al3 plus. So they are double sulfates, two sulfates. One is potassium sulfate, the other is aluminum sulfate. Double sulfates with the univalent cation and a trivalent cation. Or you can general formula you can write X2SO4, Y2SO4 thrice, 24H2. Where X is equal to Na plus, K plus, rubidium plus, cesium plus, ammonium plus. Y is equal to Al3 plus, Cr3 plus, Fe3 plus, cobalt 3 plus. So X should carry 1 unit of positive charge. Y should carry 3 units of positive charge. They are called alums. Here, very interestingly, I did not write Li plus. There is a question. Lithium do not form alum because it cannot coordinate with 6 water molecules. So please write a note. Lithium cannot form alum Lithium cannot form alum because it cannot coordinate with 6 water molecules. Suppose if you take 2 as common in this formula, this entire formula, if you divide with 2, what you will get? X, Y, total SO4s are 4 by 2 means SO4 twice 24 H2O by 2, 12 H2. This is a simplified formula of alum. What is this? Simplified formula of alum. And based on this, you have one more question. In alum, each cation is surrounded by 6 water molecules. In alum, each cation is surrounded by 6 water molecules. Next point, alums are used in water purification. Alums are used in water purification. In which the suspended impurity particles are coagulated as a precipitate. So what is the role of alum in water purification? It coagulates the suspended impurities present in the water. Coagulation means a type of precipitation. So all impurities will settle down. Next important point, alums are used as styptics or blood coagulants. So if any minor cut to your finger or while playing your game, you fell down, you had a small abrasion, blood is coming out. To stop the bleeding, to prevent the bleeding of the blood, immediately if you rub alum there, immediately the blood will be coagulated, the bleeding will be stopped. So for minor wounds and cuts, alums are used as blood coagulants. The reason is pH of blood is 7.4. Slightly basic. Slightly basic. Aqueous solution of alum is acidic. So when you apply alum application to the injured part, lower the blood pH, and the globular nature of blood protein. The globular nature of blood protein changes to fibrous protein. This is called denaturation of protein. Denaturation of protein. This denaturation you are studying in your biology as well as in the biomolecules, proteins, amino acids. There also we come across this point. Whenever the pH of a protein changes, its nature also changes. In the denaturation of protein, the primary structure is not changed. That is sequence of amino acids. Only the secondary, tertiary, quaternary structures changes. So actually before applying alum, the blood is what kind of protein? Is a globular protein. When you apply alum there to the injured part, it changes the blood pH. So blood pH, when it changes, whenever the protein pH changes, its nature also changes. That is called denaturation. So here we are covering one more point of the proteins chapter. Denaturation of protein. Now the last point regarding alums. Alums are also used as mordants. Means binding agents. They bind the dye and fabric. Dye and fabric together. So actually in the dyeing industry, cloth is subjected to different colors or different colored dyes we apply. So the color, we call it as a dye. Actually these dyes are organic molecules. They form chemical bonds with the fibers of the fabric. That's why while you're washing or keeping under sunlight, the dye won't fade away. If it is a good quality dye, the dye will last till the cloth is completely damaged. Till there, up to that time, the dye binds with the fibers of the fabric. That is a big industry, dyeing industry. I think you heard about Bombay Dyeing. It is a company, Bombay Dyeing. Nasli Wadia is the owner. So, like that, dyeing is a big industry. Even in our country, people make local dyes also. Like in Kolkata. What is the famous dye in Kolkata? Your neighboring state. In British India, there is a big agitation. Very good. Indigo. A dark blue color dye. Indigo plantation is cultivated in Kolkata, West Bengal. So like that, local dyes are also there. So sometimes the dye and fabric, they don't form bonds. Then you have to use a binding agent that binds whom? Dye and fabric together. So alums are mordants, alums are blood coagulating agents, alums are water purifiers. So alums have several applications. So here, after this point, I think we already discussed about, refer to your notes also. AlCl3 also, we discussed many points. Yes or no? Not now, long back. In chemical bonding I discussed. In chemical bonding, I discussed in anhydrous state, the bonds present in AlCl3 are covalent due to high polarizing power of Al3+. In aqueous medium, AlCl3 behaves like an ionic compound because of high hydration energy of Al3+. In vapor state, AlCl3 exists as dimer. AlCl3 fumes in moist air because it undergoes hydrolysis, liberating HCl. Do you find all these points? So that I can avoid again. AlCl3 dimer. Fajan's rules. Fajan's rules. After Fajan's rules, yes or no? It is used as a Lewis acid and generate electrophile in Friedel-Crafts alkylation and acylation. Important points related to aluminum chloride. What is that? There itself, all the other points are not there. Okay. So, anhydrous state. Anhydrous state means without water, covalent bonds are present. Aqueous medium. It ionizes. Why suddenly the covalent compound? Here covalent compound. When you add water, it is becoming an ionic compound. Just by adding water, its nature changes. Why? Because of large hydration energy of Al3+. Why it is becoming ions? Due to the large hydration energy of Al3+. Why it is covalent without water? Due to large or high polarizing power of Al3+. In vapor state, okay, please in the same chemical bond, go to coordinate covalent bond. Somewhere I strongly remember that I discussed coordinate covalent bond. Or dative bond. Yes or no? No. So in vapor state, AlCl3, here I am writing another AlCl3. So 2 units of AlCl3. Here Cl has 3 lone pairs. Whenever chlorine forms a single bond, it has 3 lone pairs. Now this lone pair is donated to this aluminium. Aluminium has a vacant orbital. Similarly, this lone pair is donated to this aluminium. So 2 units are joined together. Joined by what bonds? Whenever I write an arrow, it is coordinate covalent bond or dative bond. So in vapor state, aluminum chloride exists as dimer. Whenever 2 units are joined together, we call it as a dimer. Which is the Lewis acid here? Who is the lone pair acceptor? Aluminium. Who is the Lewis base? Chlorine. Electron pair donor. So it exists as a dimer in vapor state. In aqueous solution, aluminum ion exists as AlH2O 6 times 3 plus with sp3 D2 hybridization, octahedral shape. Octahedral. Nature of aqueous solution. Nature of aqueous solution. So the answer is acidic due to cationic hydrolysis. Due to cationic hydrolysis. In Friedel-Crafts reaction, Friedel-Crafts, it acts as Lewis acid. And generate the electrophile and generates the electrophile. Last point, in moist air, it fumes. It fumes as it undergoes hydrolysis. Liberating HCl fumes. So whenever you come across aluminum chloride, you should know this many points. Now after this, we are switching over, after mentioning all the important points. Now in the 15th group also, we have done a lot of work. Oxides also we completed. Yes or no? In oxides you write 2-3 important points. The first point is electron molecule and is paramagnetic. NO2 is also an odd electron molecule. and is paramagnetic. And reddish brown in color. This is another important point. The fourth important point, when NO2 is subjected to cooling, cool, reverse direction heat, you get N2O4 gas Actually, this is called a dimerization. When two NO2 units join together to form N2O4, what we call the process? Dimerization. Now, in the dimerization, whatever the unpaired electron present on the nitrogen, combine with another unpaired electron of another nitrogen. So, two NO2 units are joined with each other, forming N2O4 with no unpaired electrons. No unpaired electron or electrons. That's why it becomes diamagnetic and colorless. Suppose if I want to convert this into a assertion reasoning type question, I want to convert. So assertion I will give you like this. NO2 is reddish brown in color and paramagnetic, while its dimer is colorless and diamagnetic. This is my assertion. Reason, shall I repeat? NO2 is reddish brown in color and is paramagnetic. NO2 is reddish brown in color and is paramagnetic. While its dimer is colorless and diamagnetic. While its dimer is colorless and diamagnetic. So this is all my assertion. Now I will give the reason. In the dimerization process, the two unpaired electrons form a covalent bond between the two nitrogen atoms. In the dimerization process, the two unpaired electrons form a covalent bond between the two nitrogen atoms. So actually this dot I have shown here. So this dot, two dots join. Two dots means pair of electrons. When they are present separately, it is a single electron. When two units join, dimerization process, the unpaired electrons are gone now. Since there are no unpaired electrons, it is diamagnetic and colorless. Now one more point. In the solid state of N2O5 or in in the solid state N2O5, in the solid state N2O5, in the solid state N2O5 has an ionic structure. Has an ionic structure called nitronium nitrate. Nitronium nitrate, NO2 plus, NO3 minus. Solid state of N2O5 has what structure? An ionic structure, nitronium nitrate, NO2 plus, NO3 minus. But in vapor state, same structure, you can write a oxygen in between. So this is N2O5 structure. Vapor state, this structure. Solid state, ionic structure. In many examinations this question was asked. Many exams. Now write the heading oxides of phosphorus. Oxides of phosphorus Now, look at nitrogen is forming N2O with plus 1, NO with plus 2, N2O3 with plus 3, NO2 with plus 4, and N2O5 with plus 5. So nitrogen form 5 different oxides. But whereas the second element phosphorus, it only formed 2 oxides, P4O6 P4O6 with the plus 3 oxidation state and P4O10 with the plus 5. Now arsenic forms AS4O6 and AS4O10. with plus 5. Antimony forms Sb4O6 and Sb4O10. And the last element, bismuth, forms Bi2O3. So this is the summary of oxides of the 15th group. First two oxides of nitrogen are neutral. All the remaining are acidic. Both oxides of phosphorus are acidic. So arsenic and antimony oxides are amphoteric. Bismuth oxide is basic. And in periodic table we already discussed, down the group basic nature of oxides increase. Down the group, due to increase in metallic nature, basic nature of oxides increase. Now among all these, only we have two important points regarding oxoacids of phosphorus. So that is structure of P4O6, structure of P4O6, you have to write 4 phosphorus atoms as if they are tetraethyl linked, and outside externally you have to link with oxygen atoms. Oh. Oh, that is the only option. I think this arrow will be there.
Oh, I dropped everything.
Like this.
That one is in the one side. That one you cannot read.
So P4O6 structure I am drawing again. So write 4 phosphorus atoms as if they are tetraethyl linked, and write connect with externally by oxygens. Like that, externally you have to connect with oxygen atoms. Internally also they have to connect with oxygen atoms. Now it is now P4O6 over. Now each phosphorus has how many bonds? Each phosphorus has how many bonds? Your eyesight is functioning? Structurally, each phosphorus is linked with how many oxygens or how many bonds? Each phosphorus has 3 lines, 3 bonds. What is phosphorus configuration? 3s2, 3p3. When it forms 3 bonds, 3s2 pair will remain. Each oxygen has how many bonds in the structure? 2 bonds. So each oxygen has 2 lone pairs. Now the two questions asked about this, already previous JEE NEET questions are asked on this. In the structure of P4O6, each phosphorus is linked with dash number of oxygens and each oxygen is linked with dash number of phosphorus. See the structure and answer. Why you are looking at my face? In the structure of P4O6, each phosphorus is linked with how many oxygens? Very good. Each oxygen is linked with how many phosphorus? Very good. That is the answer. What are the total number of lone pairs?
4.
Total. You have to count.
16.
Very good. That is also asked as a question. There are total 16 lone pairs in one molecule of P4O6. Each phosphorus is linked with 3 oxygens. Each oxygen is linked with 2 phosphorus. 6 oxygens, 6 into 2, 12 lone pairs. 4 phosphorus, 4 lone pairs. Total 16 lone pairs are there. Correct? Now, in P4O10, write the next heading, structure of P4O10. So in the structure of P4O10, the lone pairs and phosphorus you have to erase. Remaining everything is same. Here you have to write a double bonded oxygen. This is P4O10. Here each phosphorus is linked with how many oxygens? 4 oxygens. 3 single bonded oxygens, 1 double bonded oxygen. You know, P4O10 is a good dehydrating agent. You also mentioned it is a good dehydrating agent. So when it is dissolved in water, you will get phosphoric acid. When P4O6, when it is dissolved in water, you will get phosphorus acid. So this is phosphorus acid. This is phosphoric acid. But in the oxides of nitrogen, we have one more point. This one. Brown ring test for nitrates. Brown ring test for nitrates. Same here we can copy. So the nitrate ion plus react with ferrous ion in acidic medium, and it is reduced to nitric oxide. Ferrous is oxidized to ferric plus 2H2O, 3Fe3 plus. So here it is plus 5 to plus 2, plus 2 to plus 3. A redox reaction occurs. This is the first step in the Brown ring test. Brown ring test. So Brown ring test is meant for what? For the detection of nitrates. Very important. You are going to come across again the same point in your qualitative analysis. So nitrates are best identified by Brown ring test. First step is this. Now this formed NO again react with. Second step I am repeating. FeH2O 6 times 2 plus NO. FeH2O 5 times NO two plus H2. So this is Brown ring complex. So what is the oxidation state of iron in the Brown ring complex? This is another important point. So what is the oxidation state of iron? This. So X plus 5 water molecules, 5 into 0, and NO. Here the point is, students miss this point. NO is not a neutral molecule. Already NO we discussed 15 electrons. It is an odd electron molecule. So NO loses an electron to form NO plus nitrosonium ion. So here NO, though shown as neutral, it is NO plus. So plus 1 charge plus NO is equal to plus 2. So finally X is equal to plus 1. So in Brown ring complex, iron exhibits plus 1 oxidation state. This is the only case where iron shows plus 1. What is the IUPAC name of Brown ring complex? Right. IUPAC name of brown ring complex. Penta-aqua. Penta-aqua. 5 water molecules are there. Nitroso. Penta-aqua nitroso. Nitroso means NO plus. Nitroso iron 1 ion. Iron 1 ion. So penta-aqua nitroso iron 1 ion. If sulfate is there beside iron 1 sulfate, 2 plus is there, to balance 2 plus 1 sulfate ion is enough. So actual brown ring complex is beside this sulfate will be there. So FeH2O 5 times NoSO4. That is brown ring complex. This is the actual ion of the brown ring complex. Okay. Okay, in the allotropes of phosphorus, allotropes of phosphorus. White or yellow? Red, black, scarlet, violet, but these two are not important. First 3 are very, very important. Each one has one important question in the competitive exam. Regarding white or yellow, 4 phosphorus atoms are tetrahedrally linked. This is the structure of white phosphorus. Arrangement. So how they are linked with each other? In a tetrahedral manner. So whenever there is a tetrahedron, what is the expected angle? Very good. This is the tetrahedral arrangement. So the angle should be 109 degrees 28 minutes. But in P4 molecule, the bonds are so compressed and the angle is only 60 degrees. Though the angle is expected to be very free, but because these bonds are very much compressed, so it is called angle strain. Because of this angle strain, only 60 degrees, it is a very highly unstable molecule. So white or yellow phosphorus is the most unstable allotrope of phosphorus. Why it is very unstable? Bonds are compressed. Expected angle is 109 degrees 28 minutes. Observed angle is only 60 degrees. There is an angle strain. Because of angle strain, white phosphorus is very unstable. It is always kept under water. So in the lab, if you want to see white phosphorus, it is stored in a water bottle. A white waxy solid with the smell of garlic. Suppose if you take that waxy solid out of water and keep on the table, as soon as the water layer evaporates, it suddenly catch fire and burst into flames. So it is that much unstable. It is always stored under water. So why it is that much unstable? Due to angle strain. This is one of the points they are asking in the exam. So what is the covalency and oxidation state of phosphorus in white phosphorus? What, Dr. Saab? What is the covalency and oxidation state of phosphorus in white phosphorus? What is your name? Dokcha. So Dr. Dokcha. So what, doctor? Covalency and oxidation state of phosphorus in white phosphorus. Covalency is the number of covalent bonds. Structure is already there. Each phosphorus is forming 3 bonds. So covalency is 3. Oxidation state, same atoms, no oxidation state, 0. So covalency is 3, oxidation state is 0. But if you go to the next allotrope, that is red phosphorus, actually when the animal bones contain calcium phosphate, so when dead bodies were burnt in a burial ground, so when the entire body burns out, some bones will also burn out. Some residual phosphorus in the form of white phosphorus undergoes oxidation in the air, giving a bright glow in the darkness. So during night time, if you observe, at the place of the body where the body was burnt, you can see a bright glow, and immediately people may think that it is a devil or ghost coming from that place. It is slow oxidation of phosphorus giving a bright light. It is called phosphorescence. Glowing of phosphorus in dark is called phosphorescence. Glowing of phosphorus in dark is called phosphorescence. Now white phosphorus you can also do, suppose you take some white phosphorus, like 2 chocolates you kept in your mouth, because your mouth is wet, nothing will happen, it is happy, it is surrounded by moisture. While crossing your enemy, you just spit that chocolates and just walk away. What will happen? So immediately after going used to some distance, this water layer, moisture layer will dry out and they catch fire, and it causes a big fire accident also. Generally this is one of the techniques used in the rival camps to burn other properties. But Americans are using phosphorus bombs. Even they used in Vietnam War. Saddam Hussein used in Iraq-Kuwait war. So in many Gulf wars, phosphorus bombs were mercilessly used by many armies because the phosphorus burns are very severe in nature and causes a painful death. But of course, in Vietnam War, Americans were utterly defeated because of different reasons, though they have advanced technology. But they lost the war. Vietnamese won the war. So that is a different case. Now, red phosphorus, the P4 units are joined with each other and forms a polymeric structure. So red phosphorus has a polymeric structure. Same P4 unit, but these units are linked with each other. Like these N units. This is about red phosphorus. Polymeric in nature. Dr. Dokcha. What is the covalency and oxidation state of phosphorus in red phosphorus? 3 and 0, same answer. Because one middle bond has gone, that is used to link other units. Polymeric, very stable. That's why the side of the matchbox contains red phosphorus. Side of the matchbox contain red phosphorus. Matchstick contain many things actually. A friction creating material like SiO2, an oxidizing agent like KNO3. A combustible material called P4S3. Actually, this matchsticks were introduced. The scientists have first introduced strike anywhere match. You can strike on your bald head. Or on your forehead. Or on your nail. Whenever you strike, it catches fire. Actually, for cinema people, the matchbox industry make that type of box and give it to them for shooting purpose. But after seeing the movie, if you come and again strike a matchstick on your forehead or bald head, nothing will happen. Because nowadays we are using safety matches. So on the matchbox you will have the caption, safety matches. So they will only strike when hit on the side of the matchbox. So the friction causes heat. That heat immediately undergoes combustion of the combustible material, P4S3, phosphorus trisulfide. And an oxidizing agent is there, KNO3, potassium nitrate, that supplies oxygen. But the stick which you are holding is a wooden part. So that should not, the flame should not reach your finger fast. That's why the sticks are immersed in borax. Borax is fire retardant. What is borax? Na2, B4O710H2O, sodium tetraborate, decahydrate. That is a fire retardant. Borax is also anti-termite. So for wooden sticks, wooden logs, borax is coated to prevent termites. Okay. This is about red phosphorus, stable allotrope of phosphorus. At room temperature it is very stable, is used in matchbox industry. Now regarding black phosphorus, you have only one important point, most important point. The thermodynamically the most stable allotrope of phosphorus. Thermodynamically the most stable allotrope of phosphorus is black phosphorus. Which has a layer lattice structure like graphite. Which has a layer lattice structure like a graphite. Recently we discussed a similar point. Which boron compound will have similar structure like graphite? I discussed this question. Bn, boron nitride. Boron nitride also has a graphite-like structure. This one, black phosphorus, is also having graphite-like structure. Regarding PCl3, now you write the heading, halides. Nitrogen form NCl3, phosphorus form PCl3 and PCl5, arsenic forms AsCl3, AsCl5. Antimony also forms SbCl3 and SbCl5. Bismuth only forms BiCl3 due to inert pair effect. Why bismuth cannot form a pentahalide, or even it forms, it is an unstable due to inert pair effect. Now you can say MX3 type trihalides of 15th group have pyramidal structures with one lone pair, 3 bond pairs. sp3 hybridization. MX3 type, M is 15th group element, X is halogen. So MX3 type of 15th group elements, that is maybe NCl3 or PCl3, arsenic trichloride AsCl3 or SbCl3 or BiCl3. What type of shape they have? They have pyramidal shape, sp3 hybridization and pyramidal shape. Suppose if I write MX3 type of thirteenth group, like BF3, BCl3, AlCl3, GaCl3. So in our syllabus, you come across MX3 type of halides in two groups, 13th group and 15th group. In 13th group, they are trigonal planar with sp2 hybridization and mu is equal to 0 dipole moment. They are non-polar. In 13th group, MX3 type halides are having what shape? Trigonal planar shape. What type of hybridization? sp2. Their dipole moment mu is equal to 0. They are non-polar in nature. They are non-polar. MX5 type of halides of 15th group. MX5 type of halides of 15th group are having trigonal bipyramidal shape. Like PCl5. Trigonal bipyramidal. In solid state, most important point, in solid state, PCl5, in solid state PCl5 has an ionic structure. Has an ionic structure. PCl4 plus PCl4 plus PCl6 minus. PCl4 plus PCl6 minus. This is sp3 tetrahedral. This is sp3d2 octahedral. Uh, PCl3 can be prepared by heating white phosphorus with thionyl chloride. PCl3 can be prepared by heating white phosphorus with thionyl chloride. Balancing 8, 4, 4, 2. Also given in the NCERT text. Can I move? But PCl5 is prepared by heating white phosphorus with sulfuryl chloride. These two I am giving side by side. Sulfuryl chloride. So 4 PCl5 plus 10 SO2. 10 SO2 Cl2. So why I am giving these two side by side? PCl3 SOCl2. PCl3 is prepared by using white phosphorus and SOCl2. PCl5 is prepared by heating white phosphorus with SO2Cl2. That is the only small difference. In case of PCl3 it is SOCl2. In case of PCl5 it is SO2Cl2. Write the next heading. Oxo acids of phosphorus. Oxo acids of phosphorus so total 1, 2, 3, 4, 5, 6, 7. 7 oxo acids are there. Do you have 5 more minutes? Can you spare? Yes or no? Because I think today your schedule is very hectic. Hypophosphorus acid H3PO2 with +1 oxidation state. H3PO3 orthophosphorus acid with +3 oxidation state. H4P2O5 pyrophosphorus acid. So +4 + 2x - 10 is equal to 0, x is equal to again +3. H4P2O6 hypophosphoric acid. Here the oxidation state is +4. H3PO4 orthophosphoric acid. Here it is +5. H4P2O7 again +5. It is called pyrophosphoric acid. HPO3 again +5. We call it as metaphosphoric acid. There is no other go. You have it. Now, in each oxoacid of phosphorus, this is a very important point. In each oxoacid of phosphorus, there is one POH bond and one P double bond O. This is a basic, very important point. Every oxoacid, whenever you want to write a structure, you have to write POH bond and P double bond O. That is must. Second point, if the oxidation state of phosphorus is less than +5, the oxoacid may contain a pH bond or a PP bond, a pH bond or PP bond, but not both. So actually these 2 points enough for us to write the structure. Suppose I want to write the first structure. H3PO2 structure I want to write. So what I have to write? One POH bond, one P double bond O. These are must. So what is the oxidation state of phosphorus? It is less than +5. It is less than +5. If it is less than +5, what it should contain? Either pH bonds or PP bonds, but not both. How many hydrogens we have accounted here? 1H. What is the formula? How many more hydrogens we have to write? So 2 more hydrogens. You have drawn the structure. So each oxo acid, you have to write a P double bond O and a POH. NEET aspirants are increasing. Old people are becoming more and more in number. Just now, one of my friend called. He is taking a tuition for 74-year-old RTC depot manager. RTC means Road Transport Corporation. Road Transport Corporation depot manager. He is writing NEET with you. His age is 74 years. And one of my friend is taking tuition to him. He is very regular, every day he is coming to tuition. Chemistry tuition. 74 years. Okay. Now I think you have one more class or study hour. Is it a worthy class? Can we conduct? Or you are in a sleepy mode? Tell frankly. If you are in a sleepy mode, we will conduct it tomorrow evening. Monday we will conduct. What is that? Monday 6 to 7:30 like that we will conduct. Instead of late hours. No sir, we can vibrantly listen. Like that we will conduct. I have no problem. What Dr. Doctor? Monday. He is very frank. So next one is a study hour session. The basicity of oxo acid of phosphorus. The basicity of oxo acid of phosphorus is equal to the number of OH groups present in the molecule. It's a very, very important point. Look at the yesterday's structure. Hypophosphorus acid, which we mentioned, there is one OH group, one double bond O connected to phosphorus, and 2 hydrogens are linked to phosphorus. So what are the number of OH groups in hypophosphorus acid? So its basicity is 1. Actually the formula, if you see the formula, H3PO2, there are 3 hydrogens in the formula. It looks like that we are confused. It appears that it is a tribasic acid because number of hydrogens represent basicity usually. But here it is not the number of hydrogens that decide the basicity, but it is the number of OH groups that are directly attached to phosphorus that decides the basicity. So basicity of oxo acid of phosphorus is equal to the number of OH groups present in the molecule. And write one more point. The number of hydrogen atoms, the number of H atoms that are directly linked to phosphorus represent the reducing ability of the oxo acid. It gives the reducing ability of the oxo acid of phosphorus. For example, in H3PO2, write that. In H3PO2, there are two hydrogens directly linked to phosphorus. There are two hydrogen atoms directly linked to phosphorus. Hence, it is a good reducing agent. Now, if you look at the next acid, orthophosphorus acid. Orthophosphorus acid. This one. If you want to write its structure, what is our basic thing? We have to write 1p double bond O, 1p OH. How many oxygens are over? 2 oxygens, one more oxygen is there. That is one more OH group. How many hydrogens are over now? One more hydrogen should be linked to phosphorus. This is the structure of H3PO3, orthophosphorus acid. So how many OH groups are there? That's why what is the basicity? 2. It is a dibasic acid. It is a dibasic acid. Since one hydrogen is attached to phosphorus, it is a reducing agent. But weaker reducing agent. Than H3PO2. So why it is a weaker reducing agent than H3PO2? Because in H3PO2 how many hydrogens are directly linked to phosphorus? 2 hydrogens. Here only 1 H. So here in the structure you have to observe 2 things. Whatever the number of OH groups, that indicates basicity. What are the number of hydrogens that are directly linked to phosphorus, that indicate reducing ability. Now if we go to the next one, pyrophosphorus acid. pyrophosphorus acid H4 P2O5. Here, what is the oxidation state of phosphorus? +3. Yesterday we mentioned, if the oxidation state is less than +5, the molecule may contain pH bond or PP bond, but not both. Please refer to that point in the yesterday's evening session. If the oxidation state of phosphorus is less than +5, the molecule may contain a pH bond or a PP bond, but not both. Here the oxidation rate in the given structure, pyrophosphorus acid, its oxidation state of phosphorus is +3. Thus there are pH bonds but not a direct PP bond. So the next one, hypophosphoric acid, H4P2O6. This structure. So here, this is H4P2O6. How many OH groups are there? So what is the basicity? 4, tetrabasic. If one OH group is there, basicity is equal to 1. We call monobasic. If 2 OH groups are there, dibasic. If 3 are there, tribasic. Here 4 OH groups are there. It is tetrabasic. Here the oxidation rate of phosphorus is +4, means less than +5. When it is less than +5, the molecule should either contain a PP bond or pH bond, but not both. Here a PP bond is directly present. P-P bond. Now we are going for the next one. Orthophosphoric acid. So H3PO4. It contains 3 OH groups. It is a tribasic acid. This is H3PO4. Tribasic acid. 3 OH groups are there. Suppose if I ask you, is it a reducing agent? Your answer is no, because no hydrogens are connected to phosphorus. To become a reducing agent, what you require is the hydrogens must be connected directly to phosphorus. That is the thing. Now pyrophosphoric acid, H4P2O7. Here one more point you can add. H3PO4 and its anhydride. H3PO4 and its anhydride P4O10 are good dehydrating agents. Are good dehydrating agents. Are good dehydrating agents. Suppose if a molecule contains more OH groups, the extent of hydrogen bonding will be more. If extent of hydrogen bonding is more, the molecule will get dash dash dash. What did Dr. Dokcha? Yes, more OH groups, more hydrogen bonding, because of which the molecule will get dash 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 properties. More solubility, okay, in water, okay. Boiling point increases, correct. Viscosity or syrupiness increases. Now, phosphoric acid is a syrupy liquid, a sticky liquid, or an oily liquid. Why it is an oily or syrupy liquid? Due to more extent of hydrogen bonding. Similar to glycerol. Glycerol has 3 OH groups, but glycerol is compatible to skin. That's why in winter you apply glycerin to your skin in order to not making any chance skin become dry and develops cracks. To make your skin smooth and greasy or oily, what you have to do? You can apply glycerin, a cheap liquid, or even coconut oil. In rural India, people use coconut oil only. Suppose you are rich enough, you can purchase Korean beauty creams. World's topmost. Koreans maintain that special quality of beauty creams. You want to purchase? Maybe in Delhi, Bombay, they are available. Hyderabad also I doubt. So even big metros, if rich people will be there. There they import and sell. So that is a different story. So glycerin soaps like Pierce soap. So in winter glycerin soap sales are more because people want to make the skin oily. So glycerin soap, Pierce soap contain glycerin, which contain 3 OH groups. More the OH groups, more the oiliness or syrupiness. So this is one more point regarding orthophosphoric acid. Now the last one, metaphosphoric acid, HPO3. So P double bond O, OH, one more double bond, HPO3. Metaphosphoric acid. The last one I am talking. Since its oxidation state is +5, it has no pH or PP bond. To have a pH or PP bond, the oxidation state should be less than +5. But metaphosphoric acid, you have one more important point. Usually it exists as a polymeric structure. That's why they wrote it as HPO3 three times. Means cyclotrimetaphosporic acid. So I can show like this. Potassium superoxide. Here K is +1. Each oxygen will have -1/2. Like that there are two oxygens. 2 into -1/2 become -1. And K become +1. Total neutral, electrically neutral. So potassium superoxide, rubidium superoxide, cesium superoxide. In all these superoxides, oxygen is in which oxidation state? -1/2. I think we discussed this point. In submarines, yes, anybody can recall? In submarines, potassium superoxide is used, KO2, because it absorbs carbon dioxide and releases oxygen. It absorbs carbon dioxide. Submarine is a closed vessel underwater. So the engineers, the sailors, other service personnel, when they are in the submarine, so they have to be always in the closed cylindrical vessel. So they can't come and breathe fresh air and go inside. They can't open the door because we are surrounded by water. So that's why how they get pure oxygen. There are many shelves in the walls of the submarine. They keep KO2 at all places. This KO2 absorbs, I think I already discussed this. KO2 absorbs CO2 and release oxygen. A very important point. Oxygen also shows positive oxidation states. In oxygen difluoride, OF2, it shows +2 state. What is OF2? Oxygen difluoride. In oxygen monofluoride, O2F2, it shows +1. So oxygen shows positive oxidation state when it combined with the most electronegative element, fluorine. Because fluorine is the most electronegative element in the periodic table. On Pauling scale, its electronegativity value is 4.0. Oxygen electronegativity value is only 3.5. That's why in between O and fluorine bond, the bond will move towards fluorine, or the bond pair will be pulled by fluorine. So fluorine gets -1. Of course, fluorine always -1. Fluorine always shows -1. Now in this group, oxygen and sulfur, they are non-metals. That is not a great point. But here, the most important point, the two non-metals of the 16th group of the P block, that is oxygen and sulfur, they combine with many metals and form compounds which are present in the earth crust. They are called ores. So oxygen and sulfur, they are ore forming elements. Oxygen and sulfur combine with many metals and form compounds which are present in the earth crust called ores. Which are present in the earth crust and are called ores. O-R-E-S. Hence they are ore forming elements. They are ore forming elements. Actually, these ore forming elements has a special name called chalcogens. Elements of 16th group are called as chalcogens. Actually, we should not call all the elements. Precisely, oxygen and sulfur, they combine with many metals and form the compounds of metals, which are present in the form of a compound, the form of compounds, and present in the crust. We discussed in the earlier P block. Bauxite is the important ore of aluminium. What is bauxite? Al2O3, 2H2O. Here oxygen combine with aluminium and form the ore bauxite. What is uranium ore? U3O8, called pitch blende. This is a uranium ore. Actually, Madame Curie and Pierre Curie, both are scientists. A scientist couple actually, their wife and husband. They want to extract uranium from pitch blende. So they extract it. After extraction, they want to throw the remaining waste. And very interestingly, the waste still exhibiting radioactivity. They thought, okay, some more element is hiding in this. Still it is exhibiting radioactivity after recovering uranium. So again they carefully worked for many years and able to separate one more element from pitch blende, that is radium. So after the separation of radium, still the waste shows some more radioactivity. Means they thought one more element is hiding again. Meanwhile, Pierre Curie fell from an horse cart and mysteriously died. And Madame Curie alone, she worked for some more years and separated one more element from the waste. As she belonged to the country of Poland, the element was named as polonium. So 3 elements recovered from pitch blende are uranium, radium, and polonium. That polonium is in the 16th group, with half-life is given as 13.8 days. Every radioactive element has a half-life. Human beings do not have half-life. If God permits, you have a full life of, expected life of 100 years. That is beyond science. Of course, in the West, as well as Japan, Japan is flooded with old people. People won't die there. Even in the Great Britain also, old people are too much. Because the clean environment, the good habits of food, stress-free life, so all makes their longevity. That's why the Queen of Great Britain, she had a facsimile, means a model stamp with her signature. Those who celebrate the 100th birthday, they will give a certificate with the Queen's signature stamp that God has given 100 years of age. Have some more years of life with good health. Like that they praise and give a certificate. So of course in India also, at the time of independence, Indian life expectancy is very less. It's below 60 years. Now it is almost reaching 80 plus. Because here also the medical facilities has improved, and also people are aware of health and the inoculation, that is vaccines, and good way of living. Of course, urban people, again because of their faulty way of life, have short lives. So what is this half-life, full life, that I want to distinguish? For a given radioactive element, because of their unstable nuclei, radioactive is the property of unstable nucleus. If any element has its nucleus unstable, then the nucleus want to get stability. Then it give out some particles and rays called radiations. And finally, after a long period, they achieve the stability. This spontaneous process of emitting alpha, beta and gamma rays by unstable nuclei of radioactive elements is called radioactivity. It is a spontaneous process. In thermodynamics, we have discussed spontaneous. The process which takes on its own are called spontaneous. For example, flow of heat from high temperature to low temperature. Falling of water from a waterfall is a spontaneous process. It takes on its own. You need not put an effort. Of course, some processes require initiation, then they occur spontaneously. Like the combustion of fuels. Suppose you have a vehicle, a two-wheeler or a car, whatever it is. You just have given the ignition or pressed the button. It produces a spark plug, produces spark. The fuel ignites, start burning. Once the fuel starts burning, it continues. So spontaneous processes are two types, which occur on their own, which occur continuously just by initiation. You lighted a candle, that's all. It continues to burn. The candle will give light. It is a spontaneous process. Even radioactivity is a spontaneous process. Now in radioactivity, the interesting thing is, let us say you have 100 atoms in a given sample of radioactive element, like radium. Its half-life is 16-20 years. thorium 232. So thorium 232 has a highest half-life in the periodic table, 13,900 million years. What is the highest half-life in the periodic table? Thorium. What is its half-life? 13,900 million years. So what is this half-life again? Whatever the given amount, suppose I have taken 10 grams, or earlier I said 100 atoms. So these 100 atoms, they want to lose alpha, beta, gamma rays and get stability. When 100 atoms become 50 atoms, 50 are gone. So the time required to disintegrate or decay one half of the given amount is called half-life. The given amount can be 1 kg, 1 ton or 1 gram, whatever it is. Initial amount may be whatever the quantity to become half of it. What about the remaining half? It has disintegrated in the form of alpha, beta, gamma rays. Only half is left from the initial to become half. What is the time required? That is called half-life. That depends on the nature of the element. As I said, here polonium has 13.8 days. What is the T half of radium, which is also obtained from pitch blende? 16-20 years. What is the half-life of C14 isotope? C14, 5,760 years. Carbon 14. Carbon atomic number is 6, mass number is 12. That is normal carbon. But in the nature, you have one more carbon isotope with atomic number 6 but mass number 14. That is a radioactive isotope. This C14 isotope is present in carbon dioxide. So some carbon dioxide contain C in the form of C14, which is radioactive. Plants use that C14 also and synthesize carbohydrates, which we eat. And C14 also goes into our body. Suppose when I die, suppose if bone or anything is left, after so many thousands of years also, the age of the bone can be calculated by a technique called radiocarbon dating technique. Like in Egyptian pyramids, where the dead bodies are mummified, mummification. So they apply some paste and other things. They do some surgery, remove the viscera, and some body was kept in the pyramids. So this body they also keep some food materials because they think after some days it will become again alive. In pyramid, if the mummy becomes alive, she will feel hungry. That's why they keep some food materials also. You have to see pyramids in Egypt. And you know the Giza pyramid is the world famous pyramid. So in the mummification, if you take the hair sample or bone sample of the mummy and do radiocarbon dating, how many thousands of years back the sample was kept, the scientists can easily determine. Because C14 has a T half of 5,760 years. So 1 gram C14 to become half gram, how much required? 5,760 years. Half gram to become 1/4 gram, again 5,760 years. 1/4 to 1/8. Again 5,760 years. 1/8 to 1/16. Again 5,760 years. This is the unique property of radioactive elements. Every radioactive element has a characteristic half-life period. Thus nowadays doctors are making artificial isotopes, radioisotopes with short half-lives, 1 day, 2 days, and they are used in the treatment of cancers. Radioisotopes are used for killing the cancerous tumors. But that radioisotope cannot last long time in the body. Just within 1 day, 2 days, its half-life is over. Radioiodine, iodine 131 isotope is used for thyroid cancer. I think already I discussed this. Thyroid cancer. Yes or no? Generally, thyroid problems are more common for female than male. So whenever thyroid cancer occurs, there are some symptoms, swelling of your neck, which you may not notice. Difficulty in swallowing the food. Second symptom. Sudden change in the voice. The voice become hoarse. Don't worry. So when these symptoms are there, definitely there is a thyroid problem, not necessarily cancer. It may be hypothyroidism or hyperthyroidism. So what the endocrinologist will check your thyroid levels, T3, T4, TSH, and determine what thyroidism you have. If he has any suspicion, he will take a small liquid from the neck region. He will insert a needle, a fine needle, and remove some liquid and do biopsy. Then whether it is benign or malignant, they will understand. If malignancy is there, that means the person is having thyroid cancer, which is the best cancer for human beings. Cancer, the best cancer. Because it is called the best cancer, because it won't spread to other parts of the body. Usually cancer, the problem with cancer is it spreads. But thyroid cancer only restricted to the neck region. It won't spread here and there. So the surgical oncologist will cut your neck. From here to here they will cut. Not only cut, and they will. One of my students is a surgical oncologist. In Hyderabad, he is the among top 5. Maybe 1 or 2, I don't know. Grading, but top 5. Carbon dioxide contains C in the form of C14, which is radioactive. Plants use that C14 also and synthesize carbohydrates, which we eat. And C14 also goes into our body. Suppose when I die, suppose if bone or anything is left, after so many thousands of years also, the age of the bone can be calculated by a technique called radiocarbon dating technique. Like in Egyptian pyramids, where the dead bodies are mummified, mummification. So they apply some paste and other things. They do some surgery, remove the viscera, and some body was kept in the pyramids. So this body they also keep some food materials because they think after some days it will become again alive. In pyramid, if the mummy becomes alive, she will feel hungry. That's why they keep some food materials also. You have to see pyramids in Egypt. And you know the Giza pyramid is the world famous pyramid. So in the mummification, if you take the hair sample or bone sample of the mummy and do radiocarbon dating, how many thousands of years back the sample was kept, the scientists can easily determine. Because C14 has a T-half of 5,760 years. So 1 gram C14 to become half gram, how much required? 5760 years. Half gram to become 1/4 gram, again 5760 years. 1/4 to 1/8, again 5760 years. 1/8 to 1/16, again 5760 years. This is the unique property of radioactive elements. Every radioactive element has a characteristic half-life period. That's why nowadays doctors are making artificial isotopes, radioisotopes with short half-lives, 1 day, 2 days, and they are used in the treatment of cancers. Radioisotopes are used for killing the cancerous tumors. But that radioisotope cannot last long time in the body. Just within 1 day, 2 days, its half-life is over. Radioiodine, iodine 131 isotope is used for thyroid cancer. I think already I discussed this. Thyroid cancer. Yes or no? Generally, thyroid problems are more common for female than male. So whenever thyroid cancer occurs, there are some symptoms, swelling of your neck, which you may not notice. Difficulty in swallowing the food, second symptom. Sudden change in the voice. The voice becomes hoarse. Don't worry. So when these symptoms are there, definitely there is a thyroid problem, not necessarily cancer. It may be hypothyroidism or hyperthyroidism. So what the endocrinologist will check your thyroid levels, T3, T4, TSH, and determine what thyroidism you have. If he has any suspicion, he will take a small liquid from the neck region. He will insert a needle, a fine needle, and remove some liquid and do biopsy. Then whether it is benign or malignant, they will understand. If malignancy is there, that means the person is having thyroid cancer, which is the best cancer for human beings. Cancer, the best cancer. Because it is called the best cancer. because it won't spread to other parts of the body. So that much precise treatments are available nowadays with the help of isotopes. So polonium with the T-half 13.8 days, we don't use for medicinal purposes. We use technetium 90, TC90, for whose half-life is only, I think, 8 hours. Technetium 90, half-life is only 8 hours, used for radio imaging. This is scanning, MRI scanning, some color Doppler scannings. So for all these, they inject some dye which contain technetium 90. But its half-life is only for 8 hours. So after the test, few hours, if he sits down, radiation become normal. Like that, many radioisotopes are used in the medical field nowadays. Even advanced research is going on to use more and more radioisotopes for the treatments. Now, oxygen and sulfur, they are called chalcogens because they are ore-forming elements. So what is the ore of uranium? Just now I discussed pitch blend, U3O8, which is formed by oxygen combining with uranium. What is the ore of aluminum? Bauxite, Al2O3, 2H2, which is also formed by oxygen. What is copper pyrites? CuFeS2. Here sulfur form the ore. What is pitch blend? Pitch blend. Which one? Galena is PBS. Galena is PBS. Pitch blend is U3O8. Cinnabar is there. Cinnabar is HGS. So here write some sulfur ores. What are sulfur ores? Number 1, Galena, Galena, PBS. Number 2, zinc blend, ZNS. Number 3, copper pyrites. Copper pyrites, CuFeS2. Copper glands, next one, Cu2S. I think you wrote cinnabar, CINNABAR, cinnabar. Mercuric sulfide, HGS. So in all these, whatever I mentioned, who combined with whom and form these ores? Sulfur combined with metals and form ores called sulfide ores. So in nature, the most important or most abundant, in the nature, most abundant ores are oxide ores and sulfide ores. Write one more point. Sulfur is the second most catenating element in the periodic table. Sulfur is the second most catenating element in the periodic table. Now if you consider the allotropes, which we already discussed in the earlier group. Okay, if you look at the allotropes of oxygen, you have only two allotropes, dioxygen O2, trioxygen called ozone O3. Oxygen has two allotropes. One is dioxygen O2. The next one is trioxygen O3. If you take preparation of oxygen, I already discussed about industrial preparation of oxygen in the nitrogen family. How large scale O2 is prepared? By the fractional distillation of liquid air. So here I repeat that point. Industrially O2 is obtained by the fractional distillation of liquid air. In the laboratory, methods for the preparation of O2. By heating potassium nitrate, 2 KNO3 solid, 2 KNO2 plus O2. By heating mercuric oxide, 2Hg liquid plus O2 gas. By decomposing hydrogen peroxide, H2O liquid plus O2 gas. By decomposition of silver oxide, 2Ag2O solid gives 4Ag solid plus O2 gas. By the decomposition of potassium chlorate, two KCl solid, 3 O2 gas. by the decomposition of lead nitrate. PbNO3 twice solid, 2 PbO solid, 4 NO2 plus O2. Seventh one, by the decomposition of potassium permanganate. K2MnO4 plus MnO2 plus O2. By the decomposition of O3, ozone, gas. Ninth one, by the electrolysis of acidulated water. Okay, I am going for next one. For actually all these I discussed in mass relationship, mass mole relation, mass volume relation. First topic, basic concepts of chemistry.